Okay, hi, and I guess welcome to another session with Vijay, where he'll be going over the UseDef and data flow analysis in OMR.
Okay, thanks, Philip. So yeah, let me talk first about data flow analysis today. The data flow analysis engine in OMR is really a part of the code that isn't very front and center to most people's attention. It's just this thing that's supposed to more or less work outside of the from a user's perspective. It's just supposed to work, and it's been battle tested over the years, so it's probably a good thing that people aren't in there debugging problems all the time. There's the design of the data flow analysis engine is based on virtual inheritance. So data flow analysis, there's a class called data flow analysis in the file dataflowanalysis.hpp, which is in the compiler optimizer directory. Yeah, so the data flow analysis class is the root of that hierarchy. However, there are several classes that extend it. I would put those classes that extend it in sort of two different categories. There's more or less what I would term abstract classes, but abstract classes that get more and more specialized in functionality, but aren't good enough to do anything on their own as such. And in this category, I would put things like forward DF set analysis, union DF set analysis, these sorts of subclasses, which we'll get to in due course in this talk. So they're kind of really helper classes which specialize certain functionality more and more as you go down the hierarchy, but they're not an actual analysis in and of themselves. So the second set of subclasses is the set of subclasses that are actual analyses. So in this category would be things like reaching definitions or things like liveness, analyses that you're sort of more used to from a compiler theory perspective. And so oftentimes these analyses that I just mentioned, the second set of subclasses, tend to be the leaves of the class hierarchy that's rooted at data flow analysis. And the data flow analysis, of course, is the ultimate sort of abstract class in the hierarchy. It only defines certain very high-level concepts, helper functions, and so on. It doesn't even dictate, for example, what the container will be that is used to do the flow analysis. By that, I mean the data structure that is used to represent the sets that are being flown around in the data flow analysis. So that may be a good next topic to go to, in fact. So in terms of the sets that we allow, there's really, I would say, two categories of containers or sets that we allow to be flown around. One is in the BitVector or bit set category, and that's the hierarchy that is represented by DF set analysis, forward DF set analysis. These sorts of classes are kind of representing fundamentally the BitVector type of container. And I'll explain why I say type of container shortly. We only have, to my knowledge at least, one other data flow analysis that is not BitVector or category as such, BitVector container category. And that is one of the analyses that we have driven by partial redundancy elimination. It's called exception check motion. It's a subclass that's there in partial redundancy.hpp. and it actually does a data flow analysis on lists. Its core container is a linked list, and it's trying to do various operations on those lists as we're flowing around. And perhaps that's an interesting enough topic that I will spend a couple of minutes on it eventually, but we don't need to get bogged down in that area to begin with. I think for a large majority of our data flow analyses are in the BitVector Analysis family. Originally, these classes actually used to be called BitVector Analysis and Union BitVector Analysis and Forward BitVector Analysis and so on. These were the names of these classes. However, a few years back, we renamed those to be more generic. So DF set analysis, as I was saying, or forward DF set analysis, these became the names that were used in the code. And this was because we abstracted out the notion of a BitVector itself. So there's a class, BitVector class, in the OMR code base that's used, but we also wanted it to be able to run, for example, in other cases when what you're propagating around was just a bit container. So you didn't need an entire BitVector analysis or a BitVector data structure to hold a single bit. And so there is in the OMR compiler, there's a bit container class as well. And so the idea was to allow the core engine to function sort of the same way, whether you're operating on actual BitVector class instances or on bit container instances. So if you look at the code in dataflowanalysis.hpp, there's some templatization that goes on there as well with respect to the container. So you can instantiate any of these classes that I talked about with either a BitVector or a bit container in actual fact. So that you'll see the templatization through the mention of the class container and all the APIs that you see in dataflowanalysis.hpp, or a large number of them will be written in terms of the container sort of notion or the API. So let's get back to the actual contents of these classes and how they're organized. So as I said, the data flow analysis class on its own is just a placeholder. It doesn't have a very much that's useful. All that's in there is handy routines to get at the optimizer or the compilation object or the memory allocator routines, trace option, for example, whether it's set or not, those sorts of very generic notions. And there are a few helper routines in there that give you sort of very basic, is this node aliased, or is this symbol reference aliased with that one, for example, or does this tree have any exception checks in it? Very general notions that don't have anything to do with any particular analysis as such. Then you get into the root of the BitVector analysis hierarchy or the vector container hierarchy, and that's rooted at the basic DF set analysis class, which is a subclass, an immediate subclass of data flow analysis. And this class now starts to talk about notions that are more specific, written more in terms of the bit containers. So for example, this class will have a routine called get number of bits, which of course doesn't particularly make sense for a data flow analysis, but it does make sense in this context. You'll notice a large sort of preponderance of virtual functions in this class, and that's kind of the the theme throughout the virtual inheritance this sort of virtual hierarchy that we have for the data flow engine. In particular, the kinds of things that we try to offer as virtual functions are things we think a subclass is going to override in a particular way. And most of these functions are actually overridden when you look at the sum total of the subclasses that we have in the data flow hierarchy. There's very little that isn't actually overridden somewhere. For the most part, the functions that we made virtual, we are overriding and plugging in different functionality as we go along. What are some simple sort of APIs to wrap one's head around in the sense of these virtual methods? So one is, as I said, the number of bits. How you count that differs depending on the particular analysis that you're implementing. So we offer the user or the implementer of a new data flow analysis the capability to define his or her way of getting at the number of bits. Sometimes the number of bits depends on the number of symbol references. Sometimes it depends on the number of a certain type of nodes, for example, if you're counting loads or stores or checks or something. It really depends on your own specific sort of use case, what the get number of bits returns. Then there are, as you can imagine in a BitVector analysis, as you're going through the flow, is really all about doing operations at merge points, for example, or as you're encountering new treetops, you're merging data or merging the data that's flowing through into those bit vectors. So there's a virtual method named compose that we offer, which basically allows you to take two containers and create a composition of those two containers. Now, the composition might mean a union or an intersection, and when it means a union, the compose method will be overridden in the union df set analysis class to be a union, and there's a separate class which is intersection df set analysis, which will do an intersection operation as the composition operator. There's a compose. There's also an inverse compose. It's an interesting concept if you think about it. It's the inverse, as the name suggests. And where is it useful? Sometimes when you're building up gen sets for a particular data BitVector analysis, you're saying, here's a collection of either trees or blocks, and they're all resulting in this consolidated gen set. That is the set of bits that are being generated in this section of the code. There's the sort of converse image or inverse image, which is the kill set. The kill set is the set of bits that are killed by this section of code. So if you open up any sort of conventional compiler backend textbook, all these data flow analyses are described in terms of gen and kill sets. So going back to the composition operator, when you're looking to generate a consolidated gen set, the composition operator is often handy in sort of merging two different sets as you're going along, for example. And the inverse operator is useful when you're merging together the kill sets from different treetops, for example. So it's basically intuitively, if you have union as the compose operator, you have intersection as the inverse compose operator, and yeah. So So if union says that if on any one path this property is true, let it flow through, kills need the property to be killed on all paths in order for the property to be killed. So that's the intuition behind sort of why inverse composition is an intersection when composition is a union. In the interest of time, let me keep going here. That there are fundamentally there are notions such as whether an analysis even supports gen and kill sets. Nothing forces our data flow analyses to support gen and kill sets. There's an API, in fact, on the class which says, do you support gen and kill sets? And it's a virtual method as well. And basically, if this API returns true, then then it internally sort of tries to set up the gen and kill sets, or is expected to set up those sets, and the core data flow and BitVector analysis engine will assume that gen and kill sets have been set up if you return true to support gen and kill sets, and then proceed to do its analysis based on those gen and kill sets. What is the alternative to using gen and kill sets in the infrastructure? The alternative is to walk the trees and the nodes every single time you encounter a block during the data flow analysis. So as you know, data flow analysis is really can result in iteration over the CFG, as in it can cause you to visit a particular block several times in an effort to get the solution that you're after to converge. So imagine if you were visiting a block repeatedly, you were inside a deeply nested loop, you were inside several cycles, and then you have to visit it every single time, rather than visit the whole every tree and walk every node every single time. If you had a consolidated gen set for the whole block, consolidated kill set for the whole block generated up front, when the engine gets to that point, gets to the point of the block, it can just use the gen and kill sets to generate the outset for that block, rather than painstakingly walk every node every time. So this notion of gen and kill sets is there. Some of our data flow analyses actually implement a gen and kill set, some don't. So you can look up which analyses are returning or overriding this and returning true, and see their structure and how it looks compared to how an analysis that does not return true for this. There's other virtual routines in the core classes, things like whether or the way in which you're expected to initialize a container. So, for example, if you want to initialize a container for doing an intersection operation, really the initial value ought to be all the bits set. So in other words, all ones in the bit vector, because you're going to apply intersections to it. If you had started with all the bits being 0, the intersection would get blown away as soon as you started. So the intersection, the initial value is all bits set. For union, the initial value is all bits unset. If you're going to do actual composition operations as you're going along, if you don't actually do any compositions, if you just let the value pass through, if the initial value passes through, then the rule changes as well. Just because you didn't have any thing to compose doesn't mean you should set everything, for example. So it really, these sorts of APIs are there to be used in different contexts in the subclasses that exist under the BitVector analysis, the higher level superclasses. As I said, most of these APIs are overridden in the subclasses. In fact, most of them are overridden in that first category of subclasses that I talked about, which don't even really need that much external exposure. That they're just the guts of the engine that implement sort of whether you're doing a forward bit vector analysis, a backward bit vector analysis, and then more specific, if you are a forward, is it a forward union, forward intersection, or more specific in the case of backward, are you a backward intersection or a backward union? These sorts of classes are where a lot of this stuff gets overridden. When it comes down to the leaves, as I was saying, the actual implementations of specific data flow analyses, that's usually not the place for overriding these types of routines, these initialization routines or the composition routines. Those are done for you basically by these higher level subclasses that are doing the right compose, are doing the right initialization at the right place, and so on and so forth. The idea is to make it really simple at the end of the day for a user to write a new data flow analysis. If you look at the code for many of our core data flow analysis, and I'll pick the two that are most well known in literature, Reaching Definitions and Liveness, and I encourage people to go and read those data flow analyses because they're fairly short, I would say. I mean, Reaching Definitions is about, I think it's between 250 and 300 lines right now. Liveness is a bit shorter, but it's deceptive in that that some of the logic is in another class called live variable information.cvp. But the core point that I want to make, if you go and look at those classes or any of the other quote-unquote leaf data flow classes, is that you won't find very much code in them. You'll find basically two kinds of code. One is a constructor, which generally sort of establishes what kind of analysis are you. And this is important, obviously, because how is the engine going to instantiate itself to do the right operations, right? So for example, for Reaching Definitions, if you go and look, it extends union bit vector analysis. That's what it extends. So that's a way of saying that what type of analysis Reaching Definitions is. Essentially, you've stated that by overriding or extending that particular class union bit vector analysis. So you have a short constructor, usually the most important part being which data flow class you extend, which fields specific to your own analysis you set. So if you go to Reaching Definitions.cpp, for example, you set something called the useDefInfo as a field in that class, but that's a specific sort of thing for your particular analysis at hand. Then you have a perform routine generally, which just sort of calls initialize block info and very simply calls perform analysis after that. The point of this is that you do want to offer a place for a user to actually insert diagnostics or any sort of their own logic for what they want to do up front before they launch into the data flow analysis. The data flow analysis itself is launched by a call to a routine called perform analysis, which is another one of these virtual routines, and then that activates the engine, and that's it pretty much. Perform analysis does the whole propagation across the CFG. You don't need to know what's happened at all. It just kind of magically does it for you and it generates a bunch of sets that you can then pull out afterwards and start consuming for the results of the analysis. There's a few other routines there, like how do you get the number of bits? In the case of Reaching Definitions, it returns it based on the underlying useDefInfo class. And then pretty soon it gets into initializing the gen and kill set for that particular analysis. Now this, again, is one of these operations that has to be done by the specific analysis. The general data flow engine cannot know what is the right logic to generate gen and kill sets. So anyways, you have to write this piece of code. And even there, if you look at the initialize gen and kill set info, it's actually not very complex at all. It just walks over the trees and calls initialize gen and kill set info for each node that it encounters. So it's basically a tree walker over a block. And the real guts of the logic is inside this tr::node specific routine called initialize gen and kill set info for node. So that's kind of that's as basic as it gets. For your data flow analysis, you have to define what the logic is for a given node. Nobody else can do that for you. So that's as atomic as it gets in this whole engine. So in an ideal world, you just focus on that, what you want to do for your node. You set up some of the sets that need to be set up, in particular these gen and kill sets that I talked about, and you're done, and the rest is taken care of by the superclasses that are above you. So that's in a nutshell kind of how things work. There is another complication that I wanted to mention just for some sort of completeness here, is that gen and kill sets are generally thought of in terms of basic blocks. However, if you look at the engine, the overall data flow engine, it is based on our OMR's notion of structures. So it is the engine itself operates on structures. It does not operate directly on blocks or on CFG. So the reason behind this was that we wanted to give ourselves the freedom to devise analyses where gen and kill sets are created not just on a per block basis, but in theory you could create a gen and kill set for an entire structure, and we wanted to sort of take advantage of that more powerful sort of abstraction and have gen and kill sets per structure, and therefore not have to, like I was saying earlier, if you have gen and kill sets, you don't need to walk trees and nodes within a block. If you have gen and kill sets for an entire structure, you don't need to walk any of the substructures at all. If you have the whole thing, you just process that structure as a whole based on the gen and kill sets that are there for the structure as a whole.
For sake of completeness, could you explain what a structure means in OMR?
Okay, so there's basically two kinds of structures in terms of just the classes themselves. There's a block structure and a region structure. Block structure is just a wrapper around blocks in the CFG, so it's kind of the atom, if you will, of the structure hierarchy. Region structures are more complex control flow constructs or control flow structures that are built up bottom up, so to speak. So a good example would be a loop, for example. A loop has a property that you could get into the loop from the entry. So it's single entry, the sort of the entry of the loop dominates all the cycles, and all the cycles involve that entry. So there are no internal cycles within that region. If you have a cycle in that region, it always goes through the entry of that region. So that's what a well-behaved loop is in structural terms, and so we keep track of those kinds of well-behaved cyclic structures in the sort of parlance of the OMR compiler. Those are those are called natural loops. They're well-behaved loops. There's a notion of an acyclic region structure, which is a structure that is composed of several smaller substructures, and this is recursive, by the way. So a region structure can have another region structure as a subnode within it. So an acyclic structure is one that does not have any cycles at all. It's just a collection of structures, and and the control flow between those structures is well defined, but you know that there is no cycle there. Whereas for a natural loop, obviously, you know that there is a cycle, and it will always involve the entry of the region. And there is a third class in, again, OMR compiler parlance. It's referred to as an improper region. And an improper region structure is really one that has internal cycles, meaning a cycle exists, or a cycle may exist, which doesn't involve the entry of the region. It's not a guarantee that such a cycle does exist, but if there is a chance that such a cycle may exist, then we call that an improper region, and we flag it as containing internal cycles, which means that it gets disqualified from certain kinds of analyses. So OMR compiler has a rich suite of loop optimizations. None of those loop optimizations will engage if you are dealing with an improper region. All of them will get interested, at least in taking a look if it's a natural loop, for example. Maybe I shouldn't get into it in much more detail than that here, but hopefully that's good enough for people to follow along in this discussion. And in fact, it's a good segue into where I was going with this. If you have an improper region, in other words, internal cycles in the structure, it gets disqualified from the gen and kill sets on a per structure basis. We get scared of there's something odd is happening here, and we throw up our hands and say we can't do gen and kill sets on a per structure basis if you have internal cycles and if you have improper regions. The whole notion of structure is kind of easier to wrap around from a data flow perspective going forwards, because every structure has a single entry, and the information and sort of the data that is flowing in comes in through that entry point into the structure. The whole notion of data flow becomes much messier if you're dealing with backwards flow, because a region, even a block really, is defined or can be defined as single entry, multiple exit. So going backwards, you have multiple places to enter a structure. Going backwards into a block, there are multiple successors that can flow back into the block, and so on. So things get pretty hairy if you're trying to do gen and kill sets for structures with improper regions, with multiple successors leading out from the structure or exiting the structure. There's several possible entry points flowing backwards into the structure in that sort of situation, and it becomes very difficult to create gen and kill sets to operate for backwards flow analysis. So there's an attempt at doing that in the code. I would say it's a partial attempt, and then it was abandoned because it was too difficult and it was messing up the code too much. There is also an attempt done to do gen and kill sets on a per structure basis in the forward BitVector analysis, and that is enabled and works, except if there are improper regions. I think it throws up its hands in that scenario and doesn't work. But otherwise, for well-behaved structures, it does try to use it. We were originally, when we did that sort of exploration, we were expecting more savings in compile time than we got ultimately. And some of our early results also led us to sort of get pessimistic about this whole per structure-based gen and kill set approach, because the savings simply didn't match up to the complexity that we were introducing in the code, especially in the backward case, which is what led to its outright abandonment. But even in the forward case, I sometimes wonder if it's worth the complexity that we added in the code. But it's there now, and it provides a small savings. I think from memory, it was only around a 10-ish% savings in the time that we spend in the forward BitVector analysis code. So it wasn't huge. If you didn't have any notions of wanting to do this per structure-based gen and kill, in theory, I think you could have written the data flow engine on a block basis. You didn't really need to go down the structure road if you weren't actually going to go the whole way. So you could say we've gone part of the way, and we are getting some of the benefits, so it's still worth keeping the engine in terms of structures. But strictly speaking, you could have just written it in terms of blocks and CFG as well. But then you would have closed the door firmly on ever exploring this sort of area again. The other point I will say, there are some optimizations within the engine. In particular, the structure keeps track of sort of if the last time it was analyzed, it keeps track of the inset that came in, so the information that flowed in. Whether that's forward or backward, you can just visualize it as the inflow of information into that particular block. It keeps track of the last inflow information, and if it sees the same inflow the next time, then it will just produce the same outset, which it also keeps track of. Internally, it's kind of a cache that it maintains. So it doesn't even need to operate on the gen and kill set if they're present. Obviously, if they're not present, it doesn't need to walk the trees or the nodes at all. It just says, it's the same input, provided I'm an analysis that generates the same output if given the same input, which I believe most of our analyses are in that category. If not all of them are in that category, then you just take the previous outset and you flow that along. So especially given that optimization as well, it's kind of quite effective at saving compile time anyway, and maybe that was the reason why we didn't get as big a gain when we went with gen and kill sets on a full structure sort of basis as well. That those kinds of little optimizations ate into the advantage. Now, in terms of compile time itself, we don't find these BitVector analyses classes show up prominently, I would say. I mean, obviously they're there. The data flow engines are very big compile time hog at higher opt levels, but at lower opt levels like WOM, I think we only run 1 or 2 passes that require data flow analyses. Obviously, it depends on your definition of WOM that you go with for your language in an OMR sense. But in some of the front ends that or in some of the opt strategies that I've seen, it runs no more than 1 or 2 times, even at warm, and it doesn't run at all, if I'm not mistaken, at cold. So given that a large number of methods compiled in big applications tend to be warm compiled or lower opt level, you don't see the data flow analysis very prominent, but as you go up to higher opt levels, this code is more critical. And you run several passes of things like UseDef analysis. You run several passes of things like Liveness, And then all of those other data flow analyses also come into the mix a little bit more at the higher up levels. So let's take a look quickly at an enum that exists, although I'm not sure how accurate this is or how up-to-date this has been kept, but there is a file called OMR data flow analysis.enum, which lists sort of all the analyses that I'm going to say used to exist at one point in that hierarchy. And it's kind of nice. You can see them all in one place. So there's if you go to that file, as things stand today, I'm just going to talk about how it looks at the moment. There's reaching definitions. There's available expressions, which I don't believe exist in the code anymore, but only exists in the Denim. I could be wrong about that. Then there's a bunch of data flow analyses that have to do with the PRE analysis. So global anticipatability, earliestness, delayedness, latestness, isolatedness. These are all data flow analyses that are dictated by the partial redundancy elimination optimization that only runs at hot and above generally. Then there's liveness. There's a bunch of these very generic subclasses that I talked about that aren't really analyses of their own, like basic DF set analysis and so on, but they're all listed there. You can see kind of it all itself should be self-explanatory given what I've said so far in this talk. And then there's this thing called exception check motion, which is the one I talked about, was a list-based data flow analysis. And then a few other sort of more conventional tree-based data flow analysis, like a flow-sensitive escape analysis, which we run only on Power because of that platform's unique weak memory model considerations require us to eliminate sort of memory fences more aggressively. So we're willing to pay the cost of a flow-sensitive escape analysis on that platform in particular, and we have that analysis listed here as well. The reason I'm iffy about this file and taking it too far is that I know there are some analyses that have been added for the JIT on stack replacement infrastructure or implementation. There's an analysis called OSR def analysis or sort of live range analysis. Those are analyses that initiate data flow analyses. So it's a bit like that there's a wrapper analysis class, which then invokes, say, in the case of OSR def analysis, it invokes reaching definitions. In the case of OSR live range analysis, it invokes liveness from inside that analysis. So you could say that they're not new data flow analyses as such, but they're doing data flow analysis and then using the results and massaging the results in some way. So look at this set as a mostly complete set, I would say, rather than the most accurate one, at least as I look at it, it doesn't seem to be that way. I will maybe stop there and not get into UseDef info in much detail in this talk and reserve that for the next one, and instead ask if Philip has questions or there are areas within this that he feels I should get into more in the basic data flow analysis section.
Thanks, Vijay. So a couple questions. What is the difference between the BitVector and BitContainer?
I believe, so that's not tied to the data flow engine as such. These are separate classes that are just offered in the OMR compiler. The BitContainer is just a bit vector that has only one bit set, guaranteed to be only one bit set. And so it doesn't actually allocate the OMR compiler's BitVector class. It doesn't instantiate that. It just internally, I believe, stores the number of the bit that should be set. If I'm not
okay, I see. And what kind of tracing is available for the data flow engine?
So there is tracing around. Now the question, I have to go back into the code and look at how much is enabled by default under prod versus how much is enabled only under debug. When many of these classes were implemented early on in the compiler's lifetime, when there were many bugs in this sort of area, we used to do debug builds quite regularly, and that used to enable a bunch of code that was under if-def debug. So I know for a fact that there is tracing that you get for specific sort of those leaf classes have tracing of their own for sure. So things like liveness and things like reaching definitions will print out their own information even under prod. But the base engine itself it may have its tracing hidden under debug. And if that's the case, there's really no real reason. We enable if trace sort of statements elsewhere in the compiler. I don't expect it to be such a big compile time hog that it cannot be done. In fact, more broadly, I think we should take a look at the debug, everything under if-def debug, and either delete it or enable it by default, and just deprecate that for the most part.
Okay,
Does that
thanks.
answer your question?
Yep. So if I have the high level correct, to implement a new data flow analysis, basically what you need to do is pick one of the base classes like the df set or the forward df set to, I guess, conceptually model towards what you're trying to do, whether an intersection or a union, and extend that class, and then implement the custom logics for the gen and kill sets. And that's pretty much basically it.
That's it. Yes.
Okay. Seems like I have a good summary.
And yeah, the other thing you have to select is, whether you want to use a bit container or a bit vector. Yeah, you have to pick that, as well as you have to be specific about whether you want to use a union DF set analysis, or an intersection DF set analysis, or a backward union DF set analysis, or a backward intersection DF set analysis. Those are the only 4 choices from the BitVector family that you should be extending. You shouldn't be extending superclasses above that, because it leaves things ambiguous if you think about it. Like if you just extended DF set analysis, for example, okay, what is the operation, right? Like, are you saying it's a union, or are you saying it's an intersection? That stuff is left unclear, which means you fail to inherit a bunch of routines that you would have inherited otherwise, and that would have made it convenient to interact with the core engine. You could, I guess, extend one of those higher level classes if you wanted to, but then you would have to re-implement some of the same routines that exist in union or intersection or backward union or backward intersection. There's really no good reason to do that. I don't think anybody does that. There's really those 4 that you should view as the extension points for that side of the hierarchy.
Right, that makes sense. I guess when you're implementing the custom logic for the gen and kill sets, I guess you're working at the tree level at that point, and you let the analysis take care of the flow of the data across the blocks and structures,
yes,
right?
That's right. That's right. So you work, well, again, there are APIs available, I believe, for doing it tree at a time, or doing it node at a time. So So up to you. Like some analyses may want to take matters into their own hands, analyze a whole treetop, and say, I don't need to use the hook point that exists per node. I'm just going to take matters into my own hands and walk this treetop myself, and for whatever reason. So we offer that flexibility. But if you're a very conventional analysis that just doesn't have any special treetop level processing, doesn't have any special block level processing, all of the logic is basically defined by when you analyze a node, then all you need to do is extend the node-specific routine because the tree walking and the block to treetop mapping and all that will be done automatically for you by the framework. You don't have to write that code.
Yep, that makes
Does that make
sense.
sense?
Yep. And my last question is, are there any other prerequisites to running the data flow engine? I suppose something needs to compute the structure and the CFG, etc. So how's that all handled?
That's right. So you cannot run the data flow engine without structure. The way we have designed it, as I said, I got into the reasons earlier. So you do need structure. I don't think you need anything else, though. Yeah, I don't think you need anything else. Whether you need other analyses to do a particular sort of specific analysis that you're after, that's all left up to the specific analysis to request and so on, right? So for example, if the particular data flow analysis that you're interested in prereqs value numbering, for example, then it should be your specific analysis that requests value numbering. The core engine itself doesn't require it. All it requires is structure, and it's good. The node-specific logic, the TR node-specific logic that you have probably is where that information will surface, and probably is where that will be consulted. So it should be the job of that specific analysis to request other more elaborate prereqs that it needs.
Okay, thank you. I guess that's the list of questions that I had. So I'd like to thank you, Vijay, for going over this. Hopefully we'll come out with another document describing the data flow engine, and maybe next time we meet, we could talk about how the UseDef analysis uses this engine to compute the uses and the defs.
Yeah, no problem. I'll be happy to do that. One other point, just as I was paging through the file that I had here, I'll just mention, and the last thing we talked about is that there is this other notion that we have as well of sort of these containers that a container node number pair, as you see, if you see in the basic DF set analysis class, there's a notion of a container node number pair. There's a class like that. And you may be wondering what that's for. The reason is, to begin with, this analysis was based on notion that you would calculate solution for a particular block, and then, but it would be, it could be different analysis info depending on which outgoing edge you're talking about. So imagine a forward analysis, for example. You may be flowing a different information along an exception edge to a catch block than you do to a regular edge through a regular successor through a normal edge, I mean. So there isn't necessarily, because of the nature of the block definition, single entry, multiple exit, you actually may have multiple outsets. And so this other class that you see in the code, container node number pair, tries to encapsulate that. So it says for this particular node number, think successor, this is the solution. So it has this container in it as one of the two fields. It's a pair of the node number for the successor and the container, which is the solution for that. So rather than allocate a large array, which is almost always going to be very sparse, in that a particular block only has a few successors generally, rather than have an entire array for all of the possible blocks that exist in the CFG and have it be sparse. It's just this linked list of node or container node number pairs that we have, and just maintaining the solution for each of our successors, for example. I just wanted to say that because I didn't talk about that at all.
Thanks, Vijay. I guess
no problem.
That concludes our session.
Yeah, I hope to sync up with you on the next session soon. Bye, folks.